Thank you for joining us for this broadcast of Science and the Solar Eclipse. I'm your host, Gordon Dickson. Thanks again for joining us. We are talking about the fascinating connection between science and the solar eclipse and how much solar eclipses have taught us now across the centuries. And with us is Dr. George Matzko. Dr. Matzko, thank you again for joining us on the broadcast today.
Thank you very much.
We've talked about how much we have learned about the sun, the composition of the sun, therefore the composition of the stars. And last time we talked about, during solar eclipses, we have learned a great deal about the Earth's atmosphere. And you mentioned the ionosphere and other things that were happening there. And even you were present for an eclipse in South Carolina in 2017 and actually saw the shadow bands that were there on the Earth. So this has really been an interesting discussion. How about the moon itself? Here's the moon passing in front of the sun. What have we learned about the moon as a result of solar eclipses?
So the solar eclipses have contributed to our understanding of the topography of the moon. So when the moon passes between the Earth and sun, the lunar surface is illuminated in such a way that it highlights its topographical features. As the sunlight is partially blocked by the moon, the terrain features such as mountains and valleys, crater rims cast shadows into the lunar surface. And observers on the Earth can study these shadow patterns to deduce information about the topography, morphology of the moon's surface, and helps in making detailed maps of lunar features. Mm-hmm. We also can understand something about the lunar atmosphere. I don't know if you knew that the moon had an atmosphere. But it has a very tenuous atmosphere called the exosphere. And when the sun is completely obscured by the moon during a solar eclipse, scientists can observe the faint glow of the lunar exosphere as it interacts with sunlight. Mm-hmm. And by analyzing the spectrum of this glow, remember we talked about analyzing spectrums before and the line spectra and all that, they can investigate the composition and dynamics of the lunar atmosphere, including the presence of gases such as sodium and potassium. We don't normally think of those elements as gases, but they are on the moon. And we also, solar eclipses have occasionally been associated with reports of what they call transient lunar phenomena. That's a TLP. Mm-hmm. These are short-lived changes in brightness or color or appearance of the lunar surface. And we don't understand it. We don't know how that works. But they're still studying it, trying to figure out this unusual lighting condition and how it affects the moon's surface. And so by analyzing those observations, they're trying to understand the cause of these enigmatic phenomena.
Mm-hmm. And is that the atmosphere, you were referring to it that way there, is that because of the ionization of the dust particles on the moon, or what exactly is happening there?
Yes, that's right. So the hard radiation is hitting the lunar surface and causing ionization to occur. And so you actually get a very tenuous atmosphere on the moon, especially when it's on the lit side.
Mm-hmm. In all of our discussions, we've sort of been leading up to this next question because it is considered to be one of the most significant findings during solar eclipses and was actually predicted and then proven. And that is how we've learned about the effect of gravity on starlight as a direct result of the solar eclipse. Walk us through that understanding of what we've learned historically there.
So when I was in college, we learned there were four fundamental forces. There was the strong force, there was the weak force, there was electromagnetism, and that there was gravity. But we've failed, as far as scientists have failed, trying to unify those forces together, especially gravity. Gravity doesn't appear to be a force, even though I was taught it was a force. So this goes to Einstein's theory of general relativity, and that helps us understand how gravity works. So instead of thinking of gravity as a force pulling objects toward each other, like Isaac Newton did, Einstein proposed that gravity arises from the curvature of space-time itself. So think of space-time as a fabric. And so massive objects, like you put a bowling ball on a sheet of fabric stretched out, it creates denser curves in the fabric. So think of gravity that way. So think of the mass and energy distorting space-time according to general relativity. And the more massive an object, the greater the curvature in space-time. This curvature influences the motions of objects nearby, causing them to follow curved paths. So that's our idea about what gravity actually is rather than a force. Let me talk about it in terms of what we call the principle of equivalence. One of the key ideas of general relativity is the equivalence principle, which states that the effects of gravity are indistinguishable from the effects of acceleration. For example, you go into an elevator and you push the up button and you feel heavier. You feel like you're being pushed into the floor of the elevator. Or if you're going down in the elevator, you feel lighter. Okay, you feel like you're being pushed up a little bit. And we've all had that sensation. And I think you mentioned when we were talking outside the podcast that some people, go into these airplanes and they go straight up, and then they turn over and they go straight down, and they have this feeling of weightlessness for a few minutes as they travel downward in the Earth's atmosphere. So they have the sensation of not having gravity pulling on them, but they actually are having gravity, experiencing gravity. It's just that they haven't hit hit the ground yet. Okay, they would certainly feel the gravity if they hit the ground. So in general relativity, objects move along paths called geodesics. These are the shortest paths through curved space-time. These geodesics represent the natural motion of objects under the influence of gravity. So general relativity made several predictions that have been confirmed through observation and experimentation. One famous experiment was during the solar eclipse in 1919, showing that light was bent by gravity. We call this gravitational lensing, and it provided strong evidence for the theory. And so they would look at where the position of stars in the heavens near the sun, and then during the eclipse, they'd look at the same position of the stars, and they were moved. They were moved from their original positions, apparently, because of the bending of space-time as the light was bent through the geodesic. Another thing about general relativity is Einstein predicted the existence of black holes. These are regions of space-time where gravity is so strong that nothing, not even light, can escape. And so he was the first one to propose that. And of course, that's been confirmed. We've actually have pictures of black holes today. And so Einstein's theory of general relativity revolutionized our understanding of gravity arising from the curvature of space-time.
And I remember reading that when Einstein published it, I want to say it was around 1905, 1909, right there in that, he said that the best way to test this would be during a solar eclipse. And so Arthur Eddington, May 29th, 1919, in the eclipse there, he had, as the director of an observatory, I think it was the Cambridge Observatory in Britain, he had taken a picture of the Hyades star cluster because he knew that's what would be right next to the sun during the eclipse, as he was going to photograph it from Principe off the west coast of Africa. And I remember that they said if you want to understand how much the starlight shifted, they said at a difference of 100 feet, it would be the width of a human hair. How was he able to measure that? That's remarkable in and of itself to be able to do that.
Well, they're so far away. I mean, that's really the short answer, is that small differences are magnified the further away you are from that shift. So the sun is 93 million miles away, and so small difference, small shift in curvature of space-time is going to be amplified 93 million miles away.
We have really enjoyed this discussion with Dr. Matzko, and we will continue this. We'll come back to this idea of the theory of relativity as proposed by Einstein and actually proven during a solar eclipse. Dr. Matzko, thank you very much for joining us today.
Thank you very much. I've enjoyed it.
Thank you again for joining us for these series of conversations with Dr. George Matzko. He can be reached at his website, georgematzko.com. That's GeorgeMatzko.com. The Matzko Science Ambassadors. These broadcasts are brought to you by LiveServeLead.com. Live, serve, lead, helping others succeed.